Myself, Gunjan Srivastava. This is lecture 2 for operating system. As I already told in first video, some fundamentals of operating system. In this video, I just start with some other fundamentals. So when we talk about operating system and its fundamentals concepts of operating system, we should know that all the activities which are commonly done by operating system. So objective of this lecture is understand the operating system operation, learn about the interrupts and its types, understand the DMA. DMA is direct memory access, understand the storage structure and its hierarchy, learn about the computer design and its functioning, understand the process, memory and storage activities. When we talk about the operating system operations, so some operations which are already shown in the slide, these comes under the consideration. So first is input output devices, and the CPU can execute concurrently. So sometimes it happens that some operations which are required only input output devices and some operations which are required only CPU, these all are running concurrently. So the operating system has responsibility to manage input-output processes as well as CPU processes concurrently, simultaneously, and provide resources both of the processes. Each device controller is in charge of a particular device type. When we install a new hardware, as we discussed earlier, we should use device controller, and the information of device controller always stored in the operating system. By this, operating system can control device, and it is very necessary that the device controller should be registered in operating system. Next is device controller has a local buffer. Each device controller has a local buffer, which is required when a device is having a buffer, then temporarily it can store the data before it saves the data in the hard disk. The next is CPU moves data from and to main memory to and from local buffers. The next is input output is from the device to local buffer to controller. And device controller informs CPU that it has finished its operation by causing an interrupt. So what is interrupt? Interrupt are generally signals sent to the CPU by external device, normally by input-output device. They tell the CPU to stop its concurrent activities and execute the appropriate part of operating system. So there are three types of interrupts. The first is hardware interrupts. Hardware interrupts generally generated by hardware devices to signal that they need some attention from the operating system. They may have just received some data, for example, keystroke on the keyboard, or they have just completed a task which the operating system previously requested, such as transferring data between the hard drive and memory. The next type of interrupts, we can say software interrupts. Software interrupts are generated by programs when they want to call system call to be performed by operating system. The third types of interrupts are called traps. Traps are generated by CPU itself to indicate that some error or condition occurred for which assistance from the operating system is needed. Sometimes what happens that program or process is running, is in execution state, and some error has occurred. So it is the requirement of the CPU that it should inform to the system as well as to the operating system. So it creates some traps to inform the system that some error has occurred. Interrupts are important because they give the user better control over the computer. Without interrupts, a user may have to wait for a given application to have a higher priority over the CPU to be ran. This ensures that the CPU will deal with the process immediately. When we talk about DMA, the DMA is a direct memory access structure used for high-speed input-output devices, able to transmit information at very high speed, at very high memory speeds. Device controller transfers block of data from buffer storage directly to main memory without CPU intervention. And only one interrupt is generated per block rather than one interrupt, 1 byte. So this is the block diagram of DMA controller, which is now showing on your screen. We have microprocessor connected with memory and DMA controller, and DMA controller connected with input output ports, different input output ports. And these input output ports are connected with external devices. Whereas we can see in the left side of the figure where data count and address register are connected with each other, with the data registers are connected with the data lines. Address registers are connected with the address lines, and control logics are having DMA request, DMA acknowledge, interrupt, read, and write. Storage structure. Storage structure is a term which contains main memory, secondary storage, magnetic disks. All these devices we generally use for save the data, which generally used to contain our data, is keep into the storage devices. So first is main memory, only large storage media that CPU can access. The second is secondary storage, extension of main memory that provides large non-volatile storage capacity. Magnetic disk, rigid metal or glass platters covered with magnetic recording material. Disk surface is logically divided into tracks, which is subdivided into sectors. The disk controller determines the logical interaction between the device and the computer. This is the hierarchy of storage device, where a register is a tiny device to store the data. It is very fast access memory. After that, cache comes, cache connected with the CPU for its fast access data. Next is main. Main generally used to schedule jobs which are already ready to execute with the CPU. Then electronic disk, magnetic disk, optical disk, and magnetic tapes. All these are from the electronic disk to magnetic tapes. All these disks are, we can keep it in secondary storage to save the data for longer period of time. When we talk about how a modern computer works, this block diagram comes into the picture. So where instruction execution cycle exists between memory and CPU, as well as data movement exists between the memory and CPU. Devices and CPU are having connection with input-output request, data, and interrupt. Device can directly access the memory through DMA. Symmetric multiprocessing architecture. There are, you can see that multiple CPUs are there. So CPU 0, CPU 1, CPU 2. Multiple CPUs are there, and multiple CPUs are connected with multiple registers and their caches. And these caches are connected with memory. Operating system structure. Operating system structure are divided into different categories. So first is multi-programming, which is needed for efficiency. Single user cannot keep each CPU and input-output devices busy at all time. Multi-programming organizes jobs. So CPU always has one to execute. A subset of total jobs in system is kept in memory. One job selected and run via job scheduling. When it has to wait for input-output, operating system switches to another job. The second category is time sharing. So time sharing generally used for multitasking. When we are having multitask for execution, we just provide time quantum to different tasks so that each task will be in progress. So it's a logical extension in which CPU switches jobs so frequently that user can interact with each job while it is running, creating interactive computing. Response time should be less than 1 second. Each user has at least one program executing in memory process. If several jobs ready to run at the same time, that is CPU scheduling required. If processes don't fit in memory, swapping required, and it moves them in and out to run. Virtual memory allows execution of processes not completely in memory. Memory layout of multi-program system where so many jobs are in the queue, and queue is maintained by operating system. Process management. A process is a program in execution. It is a unit of work within the system. And program is passive, whereas process is active entity. Process needs CPU, memory, input, output, files, initialization data. Process termination requires reclaim of any reusable resources. Single-threaded process has one program counter specifying location of next instruction to execute. Process executes instructions sequentially one at a time until completion. Multi-threaded process has one program counter per thread. Typically, system has many processes, some operating system running concurrently on one or more CPUs. Concurrency by multiplexing the CPUs among the processes and threads. Process management activities. The operating system is responsible for following activities: creating and deleting both user and system processes, suspending and resuming processes, providing mechanism for process synchronization, providing mechanism for process communication, and providing mechanisms for deadlock handling. Memory management. All data in memory before and after processing, all instructions in memory in order to execute. Memory management determines what is in memory when optimizing CPU utilization and computer response to users. Memory management activities consist keeping track of which part of memory are currently being used and by whom, and deciding which processes and data to move into and out of memory. Also allocating and deallocating memory spaces as needed. Storage management. OS provides uniform logical view of information storage, abstracts physical properties to logical storage unit file. Each medium is controlled by a device. Varying properties include access speed, capacity, data transfer rate, access method, sequential or random, file management system. So files usually organized into directories. Access control on most systems to determine who can access what. OS activities include creating and deleting files and directories, primitives to manipulate files and directories, mapping files onto secondary storage, backup files onto stable storage media. So all these are the references books by which you can take reference. Thank you. Thank you for watching this video. And we'll take next video in which we take some fundamental functions of operating system. Till then, bye.